to express the composition of solutions. Percent composition, occasionally. Molality, occasionally. We'll see molality being used. Molality is defined differently. Molality is defined as the moles of solute per kilogram of solvent. So let's say you have a kilogram would be 1,000 grams. 1,000 grams of water would be a liter. And so it's how many moles of solute you can put into a liter of water. This is different than molarity. Molarity is per liter of solution, so it's already mixed. This is just the pure solvent, which would be water. Okay. So let's just look at a quick example here of molality. How many grams of potassium chloride must be dissolved in 250 grams of water to make 0.400 mole out solution? So what we need to know is what is 0.400 mole out? 0.400 mole out would be 0.400 moles of pure potassium chloride, KCl, per kilogram of H2O, liquid. So if we did a liter of water, how many moles of KCl can we get in there? Well, what we have is we have 250 grams of water, which is a quarter kilogram. So if we have a quarter kilogram, then we're only going to be able to get a quarter of this in there, and so it's going to come out to how many moles? 1/4 of 0.400 would be 0.100. So we'll be able to get 0.100 moles. So if we have a quarter liter, we're only going to get a quarter of the moles in there, 100 moles. But they don't want moles, they want grams. And so we'll need the molar mass of KCl. Molar mass is here. So 0.100, well, if we have 1 mole, 74. If we have a tenth of a mole, it would be a tenth of this, so 7.455 grams. In other words, 7.46 grams is the correct number of 6 pigs. We could do this using dimensional analysis. With just dimensional. Molality, not as common. Normality, we're going to skip it entirely because normality is, if you're doing a lot of titrations, then you might use normality, but specializing it. So normality, we're going to completely skip. Normality deals with something called equivalence. For every 2 equivalents of acid, we need 1 equivalent of base. Something like that. Skip it. Might have gotten that reversed, but it doesn't matter. So we're going to just focus on molarity here, as well as percent and molality to a lesser extent. Let's do normality before. All right, oftentimes when we buy things, like for example soap, you buy the concentrated stuff. You buy concentrated soap, and then what you end up doing is diluting it. Well, we do the same thing with chemicals. We'll buy the concentrated stuff and then end up diluting it because we could save money that way, shipping. And so if we do that, then one important skill to have in lab is something called solution dilution. So you buy more concentrated stuff and you end up diluting it to what you need. And this is the solution dilution equation. The solution dilution equation is the concentrated and the dilute. We're going to relate that. So the volume of the concentrated times the molarity of the concentrated is equal to the volume of the dilute times the molarity of the dilute. So normally what I do is I rearrange this equation. And this is the solution dilution equation I usually use. The molarity of the dilute is equal to the volume of the concentrated divided by the volume of the dilute times the molarity of the concentrated. This fraction here I call the dilution factor. Dilution factor. So let's say I take one part of concentrated and make it 10 parts total. So if I take, let's say, 100 milliliters of the concentrated stuff and dilute it to 1,000 milliliters, that's a 1 in 10 dilution. A 1 in 10 dilution, 1 to 10 dilution is going to give me 1/10 of the concentration. Or 1/2 dilution. I take one part of concentrated and then dilute it to 2 parts total. So it's a 1 to 2 dilution. 1 to 2 dilution gives us 1/2 the original concentration. So this is why I call it the dilution factor. The dilution factor is one part of the original over how many parts final. And so I can guesstimate the dilution factor here. So we're taking one part of original and then diluting it to a total of about how many parts? This is a 1, 2, it looks like 1, 2, 3. It looks like a 1 to 3 dilution. A 1 to 3 dilution goes 1 up here, 3 down here. It's a 1 to 3 dilution, which means our concentration should be about 1/3 the original concentration. So this is about 1/3 this original concentration. What do we do? The amount of solute remains the same. So we have 1, 2, 3, 4, 5 solute particles. 1, 2, 3, 4, 5. It's just the amount of water, the amount of solvent changes. It makes it more dilute here. So this is why the original equation, the molarity times the volume gives us moles. So the moles of solute doesn't change. That is, moles of concentrated over here on the left equals moles of dilute. All we're doing is we're changing the amount of solvent in there, making it more dilute. There have been cases where, people have done this, like pharmacies have done this, like corrupt pharmacists. Have you heard of that? There's one pharmacist who was eventually arrested for this, for diluting all the medications. So what this person did was, if this person was on some kind of anti-cancer medication, they dilute in half and can make twice as much money. Can you believe that? Somebody whose health it was unbelievable that it actually happened. So they're getting half the concentration. Well, half the concentration is going to be effective or not? Well, anyway, this is the procedure for solution dilution. The procedure for solution dilution in the lab is this. We're going to take however many parts of original and then dilute it. Actually, this is going to be a 1 in 10 dilution. How do I know this is going to be a 1 in 10 dilution? I know because we're taking 100 parts of concentrated, 100 milliliters, and diluting it to 1,000 milliliters. So we're going from 100 milliliters of concentrated to 1,000 milliliters of dilute. That's a 1 to 10 dilution. And so the dilution factor here is this. And so I can get the molarity of the dilute is equal to, well, we start off with 100 milliliters of concentrated. Actually, you know what kind of flask this is? You probably don't recognize this flask. This flask is a very special flask. It has a very long neck, and on that long neck there's a marking, and that marking varies because it depends. Each flask is a little different. And so what they do is they fill this up and then mark it to calibrate it. So they'll fill this up with 100.00 milliliters. And so that's very precise, 100.00 milliliters of concentrated. And this is called a volumetric flask. This is very common for solution dilutions and that kind of stuff. So what we're going to do is we're going to transfer this 100 milliliters into the big flask. In order to transfer it, you got to make sure you get all of it over there. And so what they're doing is they're just rinsing, the residue or whatever else is coating the inside surface. They're rinsing this so they can transfer 100%, so it's clean here. They can transfer 100% of the concentrated in here. Once once they transfer 100% of the concentrated, then they'll just keep adding water until they get to the next calibration mark. The calibration mark is apparently here. They have to be very careful because they don't want to overshoot the calibration. If you overshoot the calibration, there's no going back. You have to dump it and start over again, basically. And so here, we get it to there, and so this is a 100 to 1,000. This is also volumetric flats, and this is very precise there, so it's 1,000. So we should be allowed 5, 6 gigs in this. Times the concentrated. Well, what was the concentrated solution? The concentrated solution is 0.100 molar potassium dichromate. So this is 0.100 molar of potassium dichromate, K2Cr2O7. And so after doing this 1 to 10 dilution, this is going to be a 1 to 10 dilution, or 100 to 1,000 dilution. And then the concentration is going to be cut by a 10. So it's going to be 0.0100 molar. So that's what they're doing there. They're just doing a 1 in 10 dilution. And we take the flasks, we could do a 1 in 2 dilution, 1 to 2.5 dilution, depending on the flask we have. We have little flasks, so we could go with a 25 and dilute it to 50. That would be a 1 in 2 dilution, 25 to 50. Dilution factor. So how many milliliters of commercial hydrochloric acid, which is 11.6 molar? So when you buy hydrochloric acid, you buy the concentrated stuff, and then you just dilute it to what you need. This is really concentrated, 11.6 molar is the total concentrate. Should you use to prepare 5.5 liters of 0.500 molar hydrochloric acid. So now they want the volume of the concentrated stuff to make a dilute solution. So we'll have to solve the equation for volume of concentrated. Volume of concentrated is going to equal the molarity of the dilute over the molarity of the concentrated times the volume of the dilute here. And so the molarity of the dilute is 0.500 molar. The molarity of the concentrated is 11.6 molar. And the volume of the dilute, how much do they want? They want 5.50 liters of dilute. So, calculate it. Would give us 0.237 liters, which is 237 milliliters of concentrated. So if we take 237 milliliters of concentrated and then add enough water to get 5.5 liters, then it works out. So if we're taking 237 milliliters of concentrated, then the balance must be water, right? But sometimes it's weird how things combine. Sometimes the volumes just don't add properly, so we just add enough water to make it 5.5 liters, 5.50 liters. Okay, the next topic, solution dilution, we use for preparing solutions. Now we're going to change subject. We're going to change subject to stoichiometry. And so how do we use concentrations in stoichiometry? We use molarities. Molarities primarily. Sometimes, though, we're not given molarities, so we have to figure out what the molarity is. Calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper-2 hydroxide. All of the copper ions in 30.0 milliliters, 0.635 molar copper-2 sulfate. Right. Well, the first thing in stoichiometry is we need balanced chemical equations. So let's go ahead and write that out. The balanced chemical equation for this is going to be sodium hydroxide and copper-2 sulfate. So let's go with copper-2 sulfate, which is CuSO4 plus sodium hydroxide. What type of reaction is this? Double replacement. So what forms here? sodium sulfate, yeah, and copper 2 hydroxide. Copper 2 hydroxide, CuOH2, plus sodium sulfate would be Ne2SO4. Balance it, we'll need 2 E's. And then copper 2 hydroxide is a precipitate, as they say here. So the stoichiometry is this. Now we can't use the nifty stoichiometry that we use for gases. But what we're going to do is we're going to start off with 30 milliliters of copper 2 sulfate solution, or no, yeah, 30.0 milliliters. So we're over here. We're at 30.0 milliliters of copper 2 sulfate solution. Now, if we're given the molarity, we can go from liters of solution to moles. And so what we're going to do here is we're going to convert this to liters of solution. And then from liters of solution, we'll go straight to moles of pure copper 2 sulfate. Now, so to go to moles, we need the molarity. The molarity is given. It's 0.635 moles. 0.635 moles of pure copper 2 sulfate, CuSO4, for every liter of CuSO4 solution. So let's just do this first part. Set it up. And so I'm going to go with 30.0 milliliters of CuSO4 solution, and then convert that to liters. 1 liter contains 1,000 milliliters. So milliliters cancel, that gives me liters of solution. If I know how many liters of solution and I know the molarity, then I can go straight to moles. Which I do. I know the molarity is 0.635 moles of pure copper 2 sulfate salt in a liter of copper 2 sulfate solution. So liters of solution cancel liters of solution, and that leaves us with moles of pure copper 2 sulfate. Well, once I have moles of pure copper 2 sulfate, then I can go to moles of pure sodium hydroxide using the mole ratio. What's the mole ratio here? Mole ratio is a 2-to-1 mole ratio. 2 moles of sodium hydroxide. Got that here. 2 moles of sodium hydroxide for every 1 mole of copper 2 sulfate. Now we're at moles of sodium hydroxide. And then we have the molarity of the sodium hydroxide. So molarities let us go from liters to moles, or moles to liters. So what we're going to do is we're going to use the molarity to go from moles to liters. So we're going to go from moles of pure sodium hydroxide to liters of sodium hydroxide solution, using the molarity. The molarity says for every liter of sodium hydroxide solution, it's going to contain 0.842 moles of pure sodium hydroxide. So that's just from the molarity. I just flipped it over. So for every liter of sodium hydroxide solution, I have 0.842 moles of pure sodium hydroxide. So the moles of pure sodium hydroxide cancel, and that leaves me with moles, not moles, that leaves me with liters of sodium hydroxide solution. But we don't want liters, we want milliliters. So let's do one more conversion, 1,000 milliliters per liter. So we'll go down to milliliters of sodium hydroxide solution. So let's figure out. 45.2 milliliters of sodium hydroxide. Actually, yeah. Do this here. 30. I just don't like that they don't show me the round off steps. So 30 divided by 1,000. I want to see what the number was before, times 0.635 times 2 divided by 0.842. Divided by times 1,000. 45.249. 45.24 milliliters of sodium hydroxide solution, which is 45.2 milliliters of sodium hydroxide solution. So in solution stoichiometry, the titration is very common, and I set up the equations for you for the titration, but we'll talk about it in this chapter here. We need a burette for titration and some indicator. The indicator tells you when to stop. We use phenolphthalein for our indicator. It tells us when the reaction's completed. This is a 1 burette titration. So what they did was they put a fixed amount of acid in here, and then they're adding the base. We did a 2 burette. In Chem 1A, you do a single burette. What the difference is this. With a single burette, if you overshoot what we call the end point, where you're supposed to stop, if you overshoot that, then you're out of luck. Basically, you trash that run and start over again. With a double burette setup like we had, if we overshoot, we just back titrate and then try it again until we get it, right? In Chem 1A, you don't have that luxury. In Chem 1A, you got to hit it right the first time. If you don't, then that's a throwaway run, and keep trying. But anyway, what happens is this: the solution starts off acidic, and basically, when we eat up all the acid, then it's going to switch to what we call a basic solution. And phenolphthalein can indicate when the solution transitions from acidic to basic. So that's what we're seeing with the pink color. Once it's basic, then it stays this color. So if you overshoot, then you don't know how much you overshot by because it just keeps looking pink. It doesn't really change much. And so we need the actual endpoint is not the color. The actual endpoint is when it transitions from colorless to colored. These are some terms that are used in titrations. It's standardized. You know what standardized means? Standardized means that you know the composition to a high degree of accuracy and precision. Like standards, you know, like the kilogram standard or this standard or that standard, then we should know what the composition is. High degree of accuracy and precision. Well, typically, if we have like a HCl solution or sodium hydroxide, in our titration, you're given an HCl standard solution. The HCl standard solution was titrated against something called a primary standard. The primary standard is you pay extra money to have something that's exceptionally pure or that you know the composition of to a high degree of accuracy and precision. In other words, you have a lot of sig figs. So standardizing is just trying to figure out what the composition is to as many sig figs as possible. All right, a 25.0 milliliter sample of an electroplating solution. Electroplating is a process where you can deposit metals on other metals like gold. They can electroplate cheaper metals on the surface with gold. Electroplating is analyzed for its sulfuric acid concentration. So we have basically we have 25 milliliters of sulfuric acid. But we don't know what the concentration is because as you're doing this electroplating, the concentration changes. And so what they're trying to do is they're trying to figure out what is the concentration of that 25 milliliters of sulfuric acid. Well, to figure that out, they're going to titrate it. It takes 46.8 milliliters of 0.661 molar sodium hydroxide to neutralize the sample, find the molarity of the acid. So a titration, just like in any stoichiometry problem, we need the balanced chemical equation first. And so let's go ahead and write out the balanced chemical equation. Balanced chemical equation is going to be, well, sulfuric acid. What is the formula for sulfuric acid? H2SO4. And we're going to react it with sodium hydroxide, NaOH. And what's going to form this? Is it like a double replacement reaction here? Right, sodium sulfate. Sodium sulfate is Na2SO4 and H2O. All right, we need to balance this. It's going to take 2 sodium hydroxides and we're going to form 2 waters. So that's balanced here. Driving forces, we're going from a stronger acid, sulfuric acid, to a weaker acid, water. So ultimately, what we're after is we want to know the concentration of the sulfuric acid. So this is like day 2 of our lab. You know, we want the molarity of the H2SO4. The molarity of H2SO4 is equal to the moles of H2SO4 over the liters of H2SO4 solution. And so we got to figure out these 2 things. So the bottom is going to come from the titration itself. How many liters of H2SO4 solution did we use in this titration? Well, we used 25 milliliters. That's 25.0 milliliters of H2SO4 solution, which is 0.0250 liters of H2SO4 solution. So that's what's going to go in here. So I know how many liters of H2SO4 are used in this titration, but I got to figure out how many moles of H2SO4 I have. The moles of H2SO4, that's going to come from stoichiometry. And here, we're going to do it like this. So what are we given? We're given 46.8 milliliters of NaOH solution. And we know the molarity, so we want to go from milliliters of solution to liters of solution. We could do that just by moving the decimal 3 over. It's going to be 0.0468 liters of NaOH solution. And then we want to go from liters of solution to moles of pure NaOH. And we'll need the molarity for that. The molarity is 0.661. So there are 0.661 moles of pure NaOH for every liter of solution. Well, we don't quite have a liter. We got a lot less than a liter of solution. NaOH solution. A lot of people drop the NaOH and just call it solution per liter of solution. Once we get the moles of NaOH, then we can go to moles of H2SO4 using a mole ratio. So up top here, this is what we're going to get. We're going to get 46.8 milliliters of NaOH solution. We're going to use stoichiometry to get that H2SO4. So a liter is 1,000 milliliters. And then I have 0.661 moles of NaOH pure per liter of solution, NaOH solution. So the solution, milliliters cancel, liters cancel, solution cancels. Then once I have moles of pure NaOH, then it's a 1:2 ratio. 1 mole of H2SO4 per 2 moles of NaOH. So the moles of NaOH cancel. And then I'm going to get the moles of H2SO4, which I'll plug in on the top here. let's see what the book did here. So they calculate 0.0155 moles of H2SO4 by this calculation. I'll plug it on the top, and then we just need how many liters of solution. So they convert 25 milliliters into liters by using this conversion factor here. Milliliters cancel, you get liters. And we end up with 0.620 moles of H2SO4 per liter of solution, or just 0.620 molar H2SO4. That's a titration problem. They also do titrations using normality. In fact, if you do lots of titrations, you'll probably end up using normality, but we skip normality. We're not doing normality. Skip normality. The last section of this chapter deals with colligative properties. Colligative just means a collection. So they're a collection of properties that all solutions kind of share. And it depends on how concentrated the solution is. These colligative properties just depend on how many particles are dissolved. Not what the particles are, but just how many particles are dissolved. One of these is like freezing point of water. Freezing point of water is 0 degrees C, but freezing point of solution is not 0 degrees C. The freezing point of solution is actually lower than 0 degrees C. So we call that freezing point depression. Freezing point goes one way, it goes to lower temperatures, but the boiling point goes the opposite way. So we call it freezing point depression, means it goes lower, but boiling point is elevated, which means it goes higher. So the boiling point of water is 100 degrees C, but the boiling point of solutions is greater than 100 degrees C. So salt water boils at temperatures above 100 degrees C and freezes at temperatures below 0 degrees C, just because it has salt particles dissolved in the water. We can calculate how much. Like, for example, salt water freezes at below 0. Well, how much below 0? How much below 0 is given by delta TF? Delta TF is the freezing point depression, how much lower it gets. And delta TF is proportional to how many molal of solute particles you have dissolved in there. KF is constant. KF is called the freezing point depression constant. Here, freezing point depression constant, KF. So what we need to know is the KF for water. The KF for water find in a book. But anyway, here they are adding a solute, like the solute particles are these purple dye molecules. And what happens is these purple dye molecules disrupt, the crystal formation. And so what it's going to do is it's going to lower the freezing point. The freezing point gets colder and colder because what happens is as ice crystals form, there's less and less solvent in there. Liquid solvent, that is, since it freezes. The ice is going to freeze as pure crystals. And so we don't get a frozen mixture. When you try to freeze a solution, what happens is the water freezes out, leaving the solute behind. Determine the freezing point of 12.0 grams of urea in 250 grams of water. Well, if we want to determine the freezing point, we need the molality. In in order to get the molality, we have to, what was the molality again? The molality, okay, so we need the molality because delta TF is equal to KF times the molality. And so the first thing is we'll try to get the molality. The molality is equal to the moles of solute particles. I would just say moles of solute over kilograms of solvent. And so we have 12.0 grams of urea. Urea is CONH2. How many kilograms of water do we have? Well, we have 250 grams of water. And so we're going to have to do some changes here. Get the units we want. And so the first thing is we need the molar mass of urea. We can calculate that. The carbon is 1201. Oxygen is 1600. We have two nitrogens. Each nitrogen is 1401, so two of them is going to be 2802. And then four hydrogens would be 404. So it's going to be 67. Here, 12, 18, 6007. Calculate. And so I can convert grams of urea to moles of urea using the molar mass. 1 mole of urea weighs 60.07 grams. Grams of urea cancel, that leaves us with moles of urea. And then I have grams of solvent, but I need kilograms of solvent, so 1,000 grams per kilogram. So the grams will cancel, leaving me with kilograms of solvent there in the water. So the first step is we need the molality. So they calculate 0.200 moles of urea and 0.25 kilograms, 0.250, and that gives us 0.800 mole out urea. Okay, so we have that. This is 0.800 mole out. Mole out, little m. Now we need KF. KF we get from the book. From the book, KF is 1.86 degrees, 1.86 degrees C per mole out. So we calculate this and it comes out to 1.49 degrees C. And so what that means is the freezing point is going to be 1.49 degrees C colder. And so the actual freezing point is going to be minus 1.49 degrees C. So this is a freezing point depression, so it's going to be that much colder. So 0 degrees is normal, minus 1.49 degrees C is going to give us minus 1.49 degrees C. Freezing point. What's this? Alright, so freezing point is going to be lower, boiling point is going to be higher. We just have to remember that. Freezing point depression, boiling point elevation. Boiling point elevation is going to be given by delta TB, KB, and M. So we need molality again, but we need KB. KB is not the same. You know, KF was 1.86. KB is more like a half a degree for water. So this is our benzene solution here, but let's calculate the boiling point of this solution, this urea solution here. And so this solution, therefore, we go 0 degrees C minus 1.49 degrees C, gives us minus 1.49 degrees C. So this urea solution will freeze at minus 1.49 degrees C, but at what temperature will this urea solution boil at? So we're going to get delta T sub B, which is going to equal Kb times little m, the molality. And so we have to look that up in the book, since I don't have it here. We'll look up the delta, the Kb for water. I don't have it here. And so,
Kb for what?
yeah, Kb for water. Okay, there's different Kbs.
The book says 0.52 degrees Celsius.
0.52 degrees Celsius. Thank you. 0.52 degrees Celsius per molal. Well, how many molal do we have? We have 0.800. 0.800 molal. Cancel that out. So what does this come out to here? So I got 0.52 times 0.416. 0.416 degrees C. Okay, therefore, this is the freezing point. Let's calculate the boiling point. Therefore, the boiling point is going to be higher than this, so it's going to be 100 degrees C plus 0.416 degrees C. So the boiling point is going to be 100.416 degrees C, or about 100.4 degrees C. And so this solution, this urea solution, is going to freeze at about minus 1.5 degrees C, and it's going to boil about 100.4 degrees C. That's for this urea solution. Any questions on that? Well, that's actually the last topic in that chapter, chapter 16. So let's just preview the next chapter. As a preview of the next chapter, we're looking at chapter 17, acid-base reactions. Chapter 17. Chapter 17 starts off talking about acids and bases. And then they talk about Bronsted acids and bases, Lewis acids and bases, the conjugates, and predicting acid-base reactions, acid-base strength. And then we get into something called the water equilibrium and pH. KW, pH, POH. pH calculations, and then that's it. So, let me start off with talking about definitions. Three definitions that we commonly use: Arrhenius, acid equals H plus AQ, or H3O plus AQ. A base equals OH minus AQ. It's Arrhenius. It turns out this is too narrow of a definition. It's too narrow. And so to broaden out the definition a little bit, come up with Bronsted-Lowry. Bronsted-Lowry definition, an acid is equal to a proton donor, and a base is equal to a proton acceptor. Still too narrow. Still too narrow. We don't get all the acids and bases that we should. And so we come up with the Lewis definition. The Lewis definition is an acid is an electron pair acceptor. And a base is equal to an electron pair donor. This is complete definition. What I mean by complete is it's broad enough to capture all of the acids and bases. It's the complete definition, or the most comprehensive. Maybe I should say complete definition, most comprehensive. Most comprehensive. And so we only need one definition. We don't just need the most comprehensive definition, the Lewis. And then we can forget about these other ones that are too narrow, like Arrhenius and Bronsted-Lowry. But it turns out that it's the most comprehensive and most difficult to work with. And so what we're going to do is we're going to break down our acids into two subsets. We're going to break down our acids into the Bronsted-Lowry type acids, and then we'll treat these as the rest. This is the easiest to work with, the easiest definition to work with. So if an acid fits this definition, we're going to use this definition just because it's easier. But if an acid doesn't fit this definition, then we have to use the Lewis. And so even though the Lewis encompasses all acids, we want to look at the acids being Bronsted-Lowry if possible, because that'll make our life a lot easier compared to Lewis. So I'll stop here.